Welcome to the 48th lecture of surface engineering. In the previous few lectures, we discussed about PVD, CVD, sputtering. So when you compare these processes, you realize that first of all, in case of PVD, you actually are conducting the processes at fairly low temperature. So in case of PVD, this is the kind of temperature range we are talking about, so up to about 450, 500 degrees centigrade, whereas in case of CVD, we are talking about anything from 500 to 1000 degree or so. So this is the CVD range and this is the PVD range. So obviously, if you are dealing with components like aluminum, copper, magnesium, all these low melting non-ferrous alloys, then the scope of application is mostly near room temperature. Certainly not elevated temperatures. So all components which are made up of these alloys, aluminum, copper, magnesium, these are usually subject to low temperature applications. But when you deal with steels, say quenched and tempered steel or carbon steel, they actually can be used not only as direct components, but also as pressure and casting molds or dies and so on. And they can develop coatings like tungsten carbide or carbon composites, molybdenum disilicide as lubricants, or diamond-like coating, or chromium nitride coatings. These are all possible through PVD processes. You can also develop, we actually seen examples where we can have titanium nitride, titanium carbonitride, titanium aluminum nitride. So the cationic, there could be doping in the cationic sublattice, or there could be dopant in the interstitial elements present in the compound. So we can have interstitial compounds. We can have interstitial compound where the cationic sites actually could also have mixtures. So obviously, elastic modulus wise, they have different range of properties and different range of utilities. When you actually want even more adherent and more wear resistant coating, higher hardness and more wear resistant coating, then you resort to these CVD processes, and you can have same thing, like you can have diamond like or silicon carbide, titanium carbide, alumina coating. And in addition, you can also have combinations of these nitrides and borides kind of coatings conducted by CVD at slightly elevated temperature. We also discussed that it's not these compounds alone. You can also have deposit of silicon or silicon dioxide, or pure elements like carbon in the form of diamond or diamond-like sp3 or sp2 type, and so all kinds of possibilities exist. The coating thickness can actually be slightly higher in case of CVD because of the chemical reaction involved. PVD coatings are usually thinner, but what is more important is that in case of PVD, the substrate deposit interface is fairly sharp. So decohesion is a possibility one needs to worry about for the PVD coated components. In case of CVD, that is less. But then on the other hand, in case of CVD, you need a big chamber, a chemical reaction, dealing with toxic gases. You have to take care of the byproducts that come out. So there are certain other disadvantages. So depending upon the scope of application, particularly the kind of materials and the end application that we are talking about, we have to choose whether we go for PVD or CVD, and accordingly the temperature of treatment also has to be decided. Before we talk about other kinds of coatings, I think it's time, since we have discussed mostly the coatings which actually within the coating or the film, the composition is the same. The composition may be different than the precursor, but the deposit that we create, the film that we create, will have the same composition throughout. That's what we have done so far in case of PVD and CVD. Of course, there is a possibility that we can alternate the layers, and we can make AB or ABC and alternate them in AB or ABC kind of coatings. But nevertheless, within the layer of A, within a layer of B, they remain the same, they maintain the same composition. But there are very many applications, and in particular, always we have discussed about either metals or semiconductors mostly, or ceramic components, but we haven't talked much about polymers. So there is a wide range of coatings possible, which are polymer-based coatings and polymer-based composite coatings. So this is what we also would like to highlight, that this polymer-based composite coatings will have a combination of two or more substances. As usual, typically that's the basis or the definition of composite. But what is important is that this matrix, the base material can be either an epoxy or a polyurethane or polyurethane or resins or various kinds of resins, and with certain dispersoids or reinforcements in that. And this primary objective is to improve the resistance against surface dependent degradations like corrosion, wear or oxidation, spoliation and so on. They find wide range of applications in oil and petrochemical industries, where you deal with parts or components like pipes or holes or pumps, valves or nozzles and so on. So what are the main benefits? We actually can induce fire and heat protection. So create a thermal barrier layer which will protect these parts from hot gas or radiant heat, or can also prevent fire or protect against fire, melting of the resin, the underlying resin, and delamination. So this is how many of these parts actually degrade. So this kind of a composite coating can actually prevent that. The coating can actually be conducting, and that's something of an advantage. Normally polymeric materials have a wide band gap, so they are not conducting, but in order to make it conducting, you can always provide a thin layer coating, and this can make it compatible to both electromagnetic and radio frequency radiations. So this is how you actually can make the polymer component conducting. The aesthetics are certainly one of the biggest advantages. You can create a ceramic or metallic finish with certain very exotic texture and color or combinations of this. You actually also can create a completely insulating layer. Heat protection I mentioned, you can also make it insulating against electrical conduction. So can make it completely insulating, electrically insulating. And so that's how you can prevent electrical shocks or any other possibilities of arcing and so on. The protections actually can give you very strong, adherent and wear or vibration resistant, these kind of protections you can induce onto the components. So applications, typically I've picked up a few examples here, like steel components, bridges, offshore platforms, underground pipelines, or all components that are used for joining them. And so you use, an application is very easy. You can apply them in the form of paints based on fluoropolymers, fluoropolymer composites, polyamide binders, thermoset, polyamide. So basically, if you are dealing with large and complex shapes and you need to apply coating periodically, for example, on the big steel bridge structures. So with the brush, you can create a paint, and that paint actually can contain these bases like polyurethane or resin base or maybe epoxy base, and have certain dispersoids or reinforcements in that, and in the process that's how you can make it highly protective against atmospheric corrosion or heat protection or fire resistant and so on. But talking about composite coating, for more sophisticated applications, what actually has really emerged as a very exciting field is the possibility of applying nanocomposite coating. Now, the application of these coatings need not be through one single methodology. They can be applied through a vapor-based technique like PVD or CVD, or even alternate sputtering or reactive sputtering, or they can be done using a laser-based deposition like pulse laser deposition, can be done even using laser surface alloying or Deposition can be done with other directed beams like electron beam, even through aqueous based coating techniques like electrodeposition or co-deposition, even sprayed techniques like plasma. What is important is now, so we are talking about a possibility that this is the component and this is the coating that we want to develop. This coating is not A alone or B. This coating is going to be A in B as reinforcement. So it's not just alloy, it's not a single layer. It actually is a single layer, but having not a single phase, it actually is a multi-phase. So this is the composite coating. Now the question is, why are we bringing in the adjective nano? So obviously we are aware of the utilities of nanometric structures, nanometric solids in bulk form or in thin films or in other possible architectures and combinations. But in case of coating, having the second phase in nanometric dimension is very useful, because in that case you gain in terms of uniformity, and also the amount that you require will be reduced. So you actually need lower amount of reinforcement if the size is ultra fine, typically submicron and few tens of nanometers. And to have them uniformly distributed and dispersed, you actually need a binder, you need a matrix. And that matrix can be a polymer, can be a metal, or can be, for that matter, any other solid, essentially which should be compatible with the reinforcement. So here is an example, it's a proprietary item. So if you have a cubic boron nitride coating already developed, in order to make this substrate or surface even more wear resistant and reduce, for example, the friction coefficient and make it more compatible, you actually can have, for example, these are the harder particles which are dispersed in a softer binder. Surprisingly, in this case, the softer binder is actually an amorphous material, silicon nitride, not in crystalline form but in amorphous form. So the harder phases are actually a mixed nitride, aluminum titanium nitride, in nanometric form. So this nanometric nitrides of aluminum titanium nitride is dispersed in this amorphous layer, which is a silicon nitride. Now stoichiometrically this may not be exactly Si3N4, but somewhat similar. So this coating actually from the top, so this is on the cross section from the front view, from the top it would appear something like this. So you will see such faceted phases, which are these aluminum titanium complex nitrides, mixed nitrides, and the matrix, which is the sort of binder, which is the continuous phase that you are seeing. So this continuous bright or white phase is basically this silicon nitride, which is in the amorphous form. And this is how you actually can get very high tool life, compared to a situation where you have no coating or only titanium nitride coating or some other combination. So in order to increase the life of such tool insert, which is a very exotic tool, exotic in the sense this can be used at a speed, at a cutting speed for which is not possible with pure metallic inserts like high sweat steel, or even coatings with certain tools with certain coatings like alumina or silicon nitride and so on. So these tool insert, the tips are coated finally with this kind of composite, nano composite coating, and these typically the dimensions of these reinforcing phases of these complex nitrides could be few nanometers. So they are ultra fine, tiny little particles dispersed in an amorphous silicon nitride matrix. So these two phases, it can be actually multiple phases. To have them in the nanocrystalline form is useful because one is very hard and the other one, the amorphous base, is relatively softer or tougher. So the advantage is that we get very high hardness. In fact, the thickness of the layer is so thin that you actually use a nano indenter with millinewton level of load application. So the range of load that you apply is very small. You indent very small depth, and when you make such very thin indentation, you actually can produce a typical stress strain curve for a very limited region. So you have a proportionality limit, and from this proportionality limit you actually can also calculate the Young's modulus. So using this nano indentation technique, one can not only measure the hardness but also the elastic modulus of the material. These materials also they produce very high temperature resistance because of the chemical nature of the deposit that you develop. It's not pure metal, it's actually compound, and these compounds have very high melting temperatures. So they are, and also are very strongly bonded compounds, so they are resistant to heating. And this is not isothermal heating, this is basically contact heating, adiabatic heating during the high speed cutting operations. And so the dimension of the tool is better retained by application of such nanocomposite coatings. A similar kind of exotic coating or a very sophisticated coating could be either diamond or diamond-like coating. Now we all are aware that in the pure form, when carbon actually carbon is present or manifests itself, we are aware that carbon has a number of allotropies, number of allotropic forms. So in a completely crystalline form, so this is typically a naturally occurring diamond, but artificially also one can create this diamond by converting graphite force them into a situation where they assume a typical diamond cubic crystalline structure, which is derived from an FCC structure but with a larger number of atoms per unit cell. But without going into those structural details, what is very important is that this diamond you will call carbon a diamond only when it has pure sp3 hybridized bonding state. So in such a situation, if it's completely crystalline, having a diamond cubic structure and having pure sp3 bond, then you have these diamond structures. This is the hardest possible naturally occurring material. Synthetically, of course, you can produce slightly harder or much harder materials like cubic boron nitride and so on. But this diamond coating is very important, but there's no necessity all the time to aim coating which is pure diamond. One can also produce a diamond-like coating, and this diamond-like coating can have a mixture of sp3 and sp2 bonding. Otherwise, typically carbon is very widely available in the form of hexagonal layered structures, graphitic layer structures. But of course, the in-plane bonding is covalent, but out-of-plane bonding is not so pure covalent, and as a result, these layers or sheets are known to provide very good lubricating effect. So graphite is never considered a very hard material. Graphite is rather a lubricant material. But the same composition, the same chemistry can be converted into ultra-hard diamond or diamond-like structures. But diamond-like, instead of diamond-like structures, what is important is to create diamond-like coatings, the diamond-like coatings. They are very similar to natural diamond, but they don't have a pure crystalline structure, and also they don't carry the typical sp3 bond. So if you have diamond-like coating on top of a component or a tool, you have high hardness, you have chemical inertness, and low coefficient of friction. So obviously these are the advantages. So if you don't need very high hardness or very high, extraordinarily high strength at the surface, you can go for this diamond-like coating, and this will still provide you so many advantages. I want to just show you an example from certain research output from our own group. This is picked from the PhD thesis of Mitun Das, who is a scientist in CSIR laboratory. Say, for example, if you want a composite coating of boride and nitride together. Now, there's no single synthesis process, a pure synthesis process, which will give you such a composite or a complex combination of a boride and a nitride both on top of a surface. So using a laser-based technique, you actually can create. So what you start with boron nitride powder and titanium alloy powder, mix them. So you pick them powders in different sizes, mix them well, and then spread it onto the surface, carry out a laser surface melting, and then in the process you can produce layered structures with very high hardness, extremely high hardness. But what is even more important is that the substrate is, for example, a pure titanium or the titanium alloy, on top whose hardness would be in Vickers scale much lower than these numbers, maybe 1/3 of these numbers or even less. But on top of that, you can produce a coating which is fairly adherent, because this is growing on the titanium substrate and then is providing you fairly thick. Now, compared to the PVD, CVD kind of vapor-based processes, these kind of laser-based processes can give you easily 0.5 millimeter or close to a millimeter thick layer, so fairly thick layer, and this is reasonably defect-free, and most importantly, very well adherent to the substrate. So, but what is also important for us to note is that we intend to produce boride and nitride, but the nitride that we develop actually is not a stoichiometric nitride, and that's possible because there are defects in the crystal itself. So crystalline defects make these kind of coatings slightly slightly deviate from the usual stoichiometry. In this approach, TiB2 was never formed, but we did form various other forms of borides. Say, for example, so the precursor is the powder mixture, and then what we develop will be various kinds of complex nitrides and boride, but not necessarily diborides. So as a result of such composite coating, you realize immediately the advantages. The Young's modulus is much higher, easily 50% higher than when you. So if you use two different levels of mixtures, if you load higher amount of boron nitride instead of 5, so this is 5 Bn and this is 15 Bn. So with a higher amount of loading, you get almost 50% higher Young's modulus, and at two different levels. So these are different laser parameters under which you produce these kind of things. So, so this kind of coating would be very useful on not only titanium-based components but also on steel to develop wear resistant coatings. In fact, wear resistance does improve significantly when you apply such coating. So the wear rate, what we realize, is very significantly decreased because of this coating, and most importantly, the hardness is exceedingly high. These are for different combinations of laser power and speed combinations. So leaving aside those experimental details, what is important is that we are able to produce such exotic combination of a boride and a nitride using such composite coating, and in this particular case, laser is the agency with which we are able to create such composite coating. We can also create similar coating of silicon carbide on titanium using a similar laser-based techniques, and so this is where you see that. So this is the substrate, and this is the coating layer that we have developed, and so you can have multiple coating layers, and this is of course the molding material. So this is the surface that you create. So this is the coating layer that you create on top of this substrate. And if you look into the microstructure of this coating, by playing with the laser parameters, you actually can make relatively coarser or much finer coatings. Now, you see, this is a silicide which is extremely hard and wear resistant, also has very high congruous melting maximum. So now you are seeing a microstructure which comprises carbides and silicides both, but you applied only silicon carbide. So the silicon carbide during the laser assisted surface engineering process intermixes and then creates these kind of combinations of carbides and silicides. So in a laser assisted process, you are able to develop a composite layer onto the surface, which otherwise is not possible by a simple deposition techniques. And the fineness of the aggregate, the microstructure, makes this whole coating much more tougher and much more adherent. So what all we discussed in this composite coating approach. So constitutionally this is different. This is not pure A or pure B. This is not an alloy. This is not a compound, but it is a combination of two or more number of phases. We found that we can have one reinforcement, or we can have multiple reinforcement like a nitride and a boride, or a silicide and a carbide, and so on. To have these components in ultrafine sizes has its utility in the form that we actually can have very uniform distribution, and hence we actually can afford to have lower volume fraction of these reinforcements and yet get a higher level of properties. The polymer composite coatings are a very, very useful material, which can be an epoxy based or a polyurethane based coating or a resin based coating, which can be applied simply with a brush or with much easier approaches or a roller and so on. And it can be applied on steel structures, on metallic structures, on ceramic structures, and so on, and can offer very good resistance against atmospheric corrosion or high temperature oxidation. Not very high, but high temperature oxidation. On the other hand, nano composite coating I just mentioned is very useful because of the uniformity and the exotic nature of the microstructure that you can develop. So nano composite coatings can be deposited from the vapor state, but more importantly, it is possible with laser based approaches. In fact, we will discuss more of these when we go into laser assisted surface engineering. Nano composite coatings can also be done using plasma, aqueous based or molten bath cladding methods, and so on. And in these processes, of course, the thickness can be much thicker than the vapor based techniques. Diamond coating is extremely one of the highest possible hardness coating that one can develop, but this is not always desirable. In that case, diamond like coating would be very, very useful. So with this, we stop here for all these thin film based coatings, and we ended with the discussion of composite and nano composite coatings. After this, we'll take up coatings or surface engineering based on direct energy beams like ion beams, laser beams, or electron beam, and so on. So thank you very much.